Thanks, Carsten, a lot for your kind introduction. It's all fine, perfectly found out everything. And yeah, so I'm a particle physicist and moved then to industry and working now as field application engineer in Europe and supporting ISVs and using FPGAs as compute accelerators. In software okay. Industry and software industry, yeah. And then my majority of my customers work in the database management system field, and so that's a very good fit. And also for the summer school here, thanks for the invitation. Salt, also thank you very much for your very kind introduction for FPGAs in general and showing a bit what kind of problems you could have when you want to offload applications to the FPGA. And I'm happy to show you a bit the interview, how the future of the technology looks like, and what could support a bit reducing the bottleneck you showed there for the interface side. So what perfect. So what I have here for today is two parts for my talk. The first is the FPGA compute acceleration part. That's the majority of the talk I will present you. There I will quickly show you what kind of acceleration cards we have. Very important message there. Intel is not producing their own acceleration cards anymore for data center qualified acceleration cards. So you have to buy now via third-party acceleration cards like Bitware and Silicom. Then I will also quickly show our newest family, the Agilex family, and also CXL interface a bit in the introduction and to what benefits it can bring us. And then as I'm working a lot with ISVs, there's the question how to enable software engineers to use FPGAs. And there from Intel, we have this Intel One API, which enables you to develop kernels in C++ in principle. And then there's a question, if you are interested to test this, where you can test this, and Intel Dev Cloud is there an opportunity. You only need your curiosity to test this. Some work, we are working with our partners together. I will show quickly, and then I go to the last part, and this is our IPUs, the infrastructure processing units. Okay, then let's get into the acceleration cards. For acceleration cards, very quickly, we talk always about PCI Express cards with an FPGA onboard memory, and you want to offload software running on the CPU to the FPGA and make this whole system faster. So what kind of technologies make also FPGAs interesting for software acceleration? One example is UPI already. So the Intel S10DX card has already UPI support where you can connect your card through the PCI Express bus to the server, and you need a server with a special motherboard where you can get a UPI cable out and connect UPI connector to the card, so that the host can also see the memory behind the FPGA, and which can here be up to 256 gigabyte DDR4 memory. And this idea will get then with CXL further continued, and so that you don't need a special cable anymore. Everything is going through the PCI Express physical interconnect, and you will get cache currency, high bandwidth, low latency interface with this. Then, because the OS is seeing the memory behind the FPGA, you can talk about memory extension with DDR4/5 with the future cards. DDR-T was always some important part of it, and we're also supporting from our FPGAs this, but what you heard already yesterday, this will be not continued. Then also interesting for caching applications, where you have to iterate over your data quite heavily. High band memory inside the package is available also for FPGAs. And there we have up to 32 gigabyte HBM2E memory in, for example, the newest Agilex M family. What you have often the problem that your kernel is larger than the resources on the FPGA, that you want to extend your pipeline and to a larger pipeline. This can be done with Intel kernel link, for example. If you're interested in this, please check the link how to connect with the network, then also several cards to one acceleration system. Then here quickly the family, the Agilex family, our newest family on the left side, the D series, which was announced just now. It's the smallest series with up to 644K logic elements. Then the F series with up to 2.7 million logic elements and supporting PCI Express 4 already. And then the I series up to 4 million logic elements, PCI Express 5, and also here already supporting with PCI Express 5, also the CXL protocol. And the M series, what you have seen just before on the bitware card, also up to 3.8 million logic elements, and there you also support then DDR5 in addition, and you have the HBM2E, and for application where you can cache the data inside these 32 gigabyte. This is very interesting, definitely. All from F, I, and M series have an integrated ARM Cortex A53. And but anyhow, you have often connected to a very performant CPU where you accelerate the software too. Then cards, as I said, in the moment you cannot buy data qualified acceleration cards anymore from Intel. So you have to go to, for example, bitware. The last data center qualified card was the D5005 from Intel, and this EA840F is the natural successor of this card. It had the largest F-series Agilex FPGA Gen 4 and PCI Express, and you can hook up to 128 gigabyte on this card. And next year, I'm also excited about using this then also soon, then the EA860M, the M series FPGA, where you have then Gen 5, 16 lanes with CXL and HBM2E and DDR5 available. Then let's go quickly in quick introduction to CXL and what kind of benefits this brings us. So for CXL, you have three. So you go over the PCI Express bus, but the physical, but you run three different protocols. You have to run the CXL IO, CXL cache, and CXL-M. And with the combinatorics, how these protocols are used, you can define different types of CXL devices. The type 1 acceleration device is in principle what we had already before, the standard acceleration card. This can have also their own memory behind, and private memory like a DDR4 or 5. And this is not visible to the OS, and but is accessible from the FPGA side. The type 2 acceleration device has in addition the MEM protocol, where you can extend the host memory with the device memory. And then you have in addition there also the type 3, which is a reduced type 2 and can be used as memory extension, where you don't have the caching part, but you can have an optional near memory acceleration with the CXL-M to the device memory. One also interesting thing, difference between PCI Express and CXL is that PCI Express attached memory is part of the MMIO space. And this is non-cacheable to the kernel-based driver invoked for any accesses there. And the CXL attached memory is different there. Here, the part is a part of the DRAM address space. So the CPU can read and write just like to DRAM via the CXL to the memory behind the FPGA. So when we look to this a bit, okay, what is new with the CXL? We have on the left side our CPU, enabling also CXL, and on the right we have the FPGA. In the center we have now the memories. So this is the memory inside the server, the host CPU attached system memory, and we have the private memory of the device. And already now via PCI Express we can via DMA from the CPU copy data to the private memory, and also the FPGA itself can access its private memory. That's good. And the CPU can also cacheable read and write to its own memory. And with USM, Universal Shared Memory, we can, from the FPGA side, via DMA, IO read and write to the host memory also. I will have a slide later also showing a bit more how to do this in one API, which is already possible even with Stratix 10. And now with CXL, you get these additional device attached system memory. So this is then visible to the OS of the CPU as a new NUMA node. This is the memory behind the FPGA on the card. And you have these 3 cacheable read and write. So 2 for the FPGA in addition, so that you can cacheable read and write to the system memory. You can cacheable read and write to its device memory, which is in principle parallel to what we have the private memory here. And the CPU can also read and write cacheable to this device memory. And this makes this much more flexible and accessible, what kind of opportunities we get now with these new interface. So the Intel Agilex implements the CXL with a hard IP, the R-tile. And this hard IP for CXL supports and is running on PCI Express 5 with 16 lanes. This supports CXL across multiple CPUs. So it's important that you have a CPU which supports CXL. That is the limitation factor there for this R-tile. CXL 1.1 is right now then supported at the beginning. And in the future, it's a new IP which you need. This same silicon can be used, the R-tile silicon. So you don't, if you have now already an R-tile FPGA, also R-tile Agilex FPGA, then you don't have to replace it because only the IP has to be updated for version 2. So, and this hard IP supports then type 1, type 2 accelerators, and also type 3 memory expansion. So then, okay, how to enable now, if you're a software engineer, you don't know, or you have not worked with FPGAs so far, and you heard that there's a large burden to work with them. There, I would like to introduce one API quickly to you, which enables you with normal data parity C++ to also write kernels on FPGA and get running very quickly. So the idea behind one API that you have the programming challenge that you have normally your CPU, GPU, FPGA, and other accelerators. Each of them have their own programming model. And with this programming model, you need own training, licenses, debugging, monitoring, maintenance. And this all limits you a lot. What can you, how you can port algorithms between the devices. And to have a one united programming model would be helpful for this. And this is the target of the one API in general from Intel. So it's not for our FPGA only. And for FPGA, it's replacing what we had before, the OpenCL. And it's now also synced in with the GPU and AI and CPU strategy for one API. This should enable the developer a common developer experience for all devices, and you can implement this in high-level language, which makes this very handy then. So for this looks now like this, that you have your devices. You have one programming model, which also adds your compatibility tool, language libraries. Also that you have, for example, if you have a library for an algorithm in one API, that you can also port it between the devices quickly. And also very important, analysis and debugging tools. For example, vTune is very important also for software engineers to find bottlenecks inside your software. And now also with one API, you can use vTune to do the same for the kernel code inside the FPGA. And also what you then do for FPGA, that you have emulation and reporting. The emulation is something which is completely running on software only, and where you can test the functionality. And with the reporting, you get then out of this some optimization report where you can improve the performance of your code for the kernel. So when we look now, how does it really look in reality now? You have here an example from FPGA add kernel and vector add kernel. And you have the application scope, you have the command group scope and the kernel scope. The application scope is completely running on the host only. The command group scope is controlling and submitting data, so controlling the accelerator and also transferring the data between host and CPU with these accessors and buffers. And the kernel scope is completely what is then running the functionality which is running inside the FPGA. In this case, as I said, you can also do this on one GPU or other CPU. And the application scope and the command scope, you can use the full capability of C++. In the kernel scope, which is in the nature for the FPGAs, you're unlimited. For example, you cannot use recursive code because the compiler has to implement it on hardware on the FPGA, and therefore it is not possible that you can use this kind of programming style. A quick introduction to vTune. And so this is also then working very easily. You have only to add to your compile command the X profile flag. And after compilation, what the compiler is doing, he adds performance counters in your code automatically in the FPGA. And with vTune, you can read out this, and after your bitstream is created and you're running on the FPGA, you only have to start vTune then, run your application with root rights and select CPU FPGA interaction. And with this, you get then a kernel schedule and in respect to the host code also view, where you can also see what is the FPGA utilization, which kernel is started when. And this is so people using vTune is very familiar to them, and but extend this now with FPGA functionality, and you can also then see like PCI Express bandwidth, DRAM bandwidth to check where are your system bottlenecks. So also these performance counters, you can then also read out inside the kernel, and where you can see how high is for some loops your utilization, what is the bandwidth through this loop. And then this is very nice also to optimize then your performance. And this is easy for software engineers also to use. You don't have to implement something in RTL there. Important to mention, if you want to implement something in RTL, this is not an issue. You can do this. You can wrap your RTL blocks into one API library functions and use then library called to use your functionality also inside one API. Yeah, here one example of this universal shared memory, which is already available now also. And this for the universal shared memory, the FPGA takes care about the data transfer. That means the CPU only creates input and output buffer, and the FPGA gets a pointer in the host memory and is doing all the data transfer. So CPU is completely offloaded from this. And you can see here, for example, this is a kernel example for a parallel add kernel. And it's also it's completely C++ to implement this kernel. And you can directly use the host pointer inside your kernel. And another advantage is of this universal shared memory that you can control when and how the data transfer happen. Without the USM, you have to use buffers and accessors in one API, what we had seen in the first example. And then the cycle runtime controls when the data gets transferred. Here's some interface bandwidth performance numbers for our D5005 card. And here you can see with PCI Express, you reach up to 12 gigabyte per second. For the onboard DDR4, when you use one channel, you reach up to 22 gigabyte per second. And when you use all 4 memory channels, you can stream through your kernel with 70 gigabyte per second. And CXL bring us there. So from PCI Express Gen 3 to 5, we go up to 40 gigabytes. And this is our expectation where we will end then with a bandwidth. This is really the throughput. We read and write then at this speed. If you want to get started, then you need the OneAPI base toolkit. This is already enough when you only want to run in emulation mode. So when you want to only check how this kernel could look like in an FPGA, this you can do already with the base toolkit. If you want to build a bitstream, then you need Quartus, and this is then included into these add-on FPGA tool, and you need also the board support package, which you get from the vendor, like the Bitware, for example. And this BSP has all the interfaces already for you set up. So the PCI Express, the DDR4, for example, or the network connector. And this is an all encapsulated that you can concentrate only developing on your kernel, the functionality inside the FPGA. If you want to learn more about data parallel C++ and how to use it, there's a free book to download from Springer. And also on the Intel webpage, there are many trainings and modules to check how this can be used. Then here is, I want to quickly introduce you to the Intel Dev Cloud, which makes it for you possible to test hardware without having hardware. You don't have to set up any environment or install OneAPI. It's all already on the servers implemented. You only have to register and you get an account for 120 days. And with this, you can test them directly and get started. So all the hardware and software is already enabled for you. And this is also nicely easy to be used. You can connect to the Dev Cloud via the gateway via SSH, or you can use Jupyter notebooks to log in and then execute commands. There's a job queue where you submit your jobs to, so that for the compilation, for example, there's a compute-intensive task is there are strong machines which can do this synthesis then quickly. And then you get your bit stream back, and then you can forward this in a queue also to a machine which has a real FPGA in there. And there you get the result back from your test. There's one drawback, that's the session timeout is 24 hours. So if you have a very large kernel, for Stratix 10, for example, then you could come into the ballpark of this compile times. And then the session gets killed. So this is a bit of a disadvantage, but yeah, normally for getting started and implement something quickly at the beginning, it's not an issue with these 24 hours. In our Git repository, there are many examples and tutorials how to use OneAPI and also for FPGA. And this is in Dev Cloud already available. So far it's still OpenCL, but OpenCL is deprecated. So soon it will be only OneAPI. And from the devices, we have ARIA 10, Stratix 10 devices there. And soon we will also have the Bitware Agilex cards in there. So then here are a few examples. There are a large number of examples, like data compression, image compression, file parsing, database acceleration, genomics, financial. For example, here also some papers of Jonas and Robert. Thanks a lot. Also there with a nice work. And there are many use cases for FPGA compute acceleration, also especially in the database management area. Check what is possible then also with the new devices for you. Then I come already to the end, and this is now the Intel infrastructure processing units, so-called IPUs. There, Intel has also an ASIC, Mount Evans. This was developed with Google. I will not show you this, but the FPGA-based IPUs I wanted to introduce to you. So we have two platforms there. One platform is C5000, where you have a PCI Express Gen 4 with Stratix 10, a Xeon D, so a small Xeon. And you have also 20 GB of DRAM on this board. For your workload inside the FPGA, you have to use RTL for this. And the target workloads are here for packet processing Open vSwitches. And the F2000 is in the new version coming next year. And there you will have 2 times 100 gigabit Ethernet connectivity. So here on the other card was only 2 times 25 gigabit Ethernet. You will have an Agilex FPGA, Intel Xeon D, a new version, so it's an Ice Lake Xeon D, and a 32 gigabyte DRAM. Here, in addition to the RTL, also P4 flow will be supported in the future. And here also the target workloads getting larger, and also examples will be available for NVMe over Fabric, security isolation, crypto, RDMA, and Rocky V2. Yeah, then I come already to my summary. So FPGA accelerator moved closer to the CPU with CXL, so this is getting really interesting and reducing a bit the burden. Also, Sultan showed in the morning in his presentation that moving the data is not so nice. The FPGA interface bandwidth is increasing faster than compute capacity right now. With Intel One API, you can also, without a lot of FPGA knowledge, test and use these devices. Also, a lot of industry standard debugging optimization tools available. Test it easily in a dev cloud. And yeah, thank you very much for your attention.